Here we are. I would like to, I'm very grateful to be invited here to talk about our research. And this is mostly to try to use integrated systems for thin film deposition in understanding energy materials, and we have a set up at our lab in Darmstadt, but we also use a lab at the synchrotron source. For that, we travel around with the car, getting parts of our deposition chambers moved to the synchrotron, and at the end, we want to know how the energy diagram of energy converting systems look like, because they dominate the performance of the systems which we are interested in. The outline of the talk will be that I will give a short introduction for the need of thin film materials for advanced renewable energy systems. Then I will shortly introduce our experimental approach, these integrated cluster systems. Then I will talk about advanced thin film solar cells, photoelectrochemical cells for fuel production, and probably I will not be able to talk about lithium intercalation battery materials because of the lack of time. And finally, I would like to conclude that there's still a lot of work to be done for thin film people in future energy technologies, and I think there's a bright future. We just need to go ahead. Okay, if you look at the energy resources used today, then you've noticed that most, I say it's in German, but that most of the energy carriers are based on fuels. It means there's only 1/3 which is related to electricity, and if we go now to photovoltaics or wind energy and produce electricity, we have the problem that this doesn't fit completely to the needs of the society. That means we have to consider chemical fuels as a future way to go, because we need to store and carry the energy sources around. Just a figure which everybody knows, that means this is the just used amount of energy for a year, and this is the amount of solar energy which we have available in a year, and this is the amount of wind energy which we have available. That means there's a lot or more than enough energy for our demands. However, if you look how the primary energy will, let's say, can be used in a typical month in Germany, this is the need of energy, this red fluctuating power, and here we have in yellow the amount of solar energy, and here in blue the amount of wind energy. This is based on for electrical energy, and then we see there are certain areas there's a lack of energy, and there are some other areas where we have a surplus of energy, which again tells us that we need to go to fuels for the transport of energy, and we need to go to fuels also for the storage of energy. It means in the long run we need something like a holy grail of renewable energy research. That means solar fuels based on hydrogen. It means we'll have an electricity cycle where we can, with photovoltaics and wind energy, and maybe with batteries, we can use electrical energy. But it would be nice to have a hydrogen cycle attached to that, where we can use then the electric energy to split water into hydrogen and oxygen, or we can do this directly by photoelectrolysis cells. And if we want, we can still add CO2 to the hydrogen and produce designer fuels, which then will be the same thing what we do and use nowadays, but this is mostly based on a renewable primary source. It means this defines also research topics which we have in Darmstadt. These are thin films and interfaces for renewable energy systems. It means we work on thin film PV, starting with copper, indium diocyanide, and on cadmium telluride, and a number of other materials. Then we worked recently, again, very much on photoelectrochemical hydrogen cell producing systems. And we also work on lithium-ion batteries, which is also a way to store energy, but maybe not in the amount which is needed for overcoming the problem with the surplus and the lack of energy from, let's say, winter times to summer times. How do we do our experimental research? As we use integrated systems, that means we have a number of film deposition chambers coupled to a circular chamber and then a number of analysis, ultra-vacuum surface science, analytical tools. And we do this because we want to get a detailed insight what we do in the preparation of our materials and what we do get as physical and chemical properties of the materials which we use. It means this is a typical system which we call DAISY-MAT, Darmstadt Integrated System, in this case for material science. And we have a number of different deposition techniques which we choose according to the needs which we have. And we couple this then to an XPS system or maybe also to a glove box system or whatever. We have also an electrochemistry chamber where we can do electrochemistry under controlled condition. And then without any contamination from the outside can transfer the samples and have a detailed insight of what happens. Mostly we use photoelectron spectroscopy as an analytical tool because it's very flexible, but we also use other techniques. And we have a number of DAISYs in our group for different applications because you wouldn't like to mix the systems too much, because if you sputter sulfur, you wouldn't like to sputter oxygen at the same system. And this is, let's say, an outlook of a system like that. That means you have here the circular distribution chamber and here the number of different deposition techniques. Usually we try to build them up by ourselves because it's, of course, a lot cheaper. We are poor people from the university. On the other hand, we can also then design them to the needs what we want to have. We use mostly surface science techniques to learn something about the properties of the surfaces and interfaces. Here we have electron spectroscopy, where we can get detailed about electronic structure, crystalline structure, chemical structure, and potentials. We have this different type of sputtering techniques where we can learn something about interdiffusion, element distributions, dopant profiles, or graded junctions. And we also use this multi-probe, atomic probe technologies to learn something about structure, morphology, and potentials. And as I've already said, we have a setup at BESSY, the synchrotron source, which is called solid liquid analysis system because it was originally designed to look at electrochemical interfaces, which we do electrochemical experiments, and then this setup is somewhere here on the top, and then transfer the samples to the measuring setup. But we also transport our deposition chambers to the system there. That means we can deposit the film materials in a similar way as we do it at home and have them in the same condition for analysis. And this is the electrochemical setup where we have, let's say, a free electrode geometry under controlled atmosphere. There's a buffer chamber to avoid that we have a contamination of the vacuum system. And yeah, usually we do it like that the sample is on the bottom. We put the electrolyte from the top to avoid carbon-hydrogen contamination, which you would have otherwise. And this is a picture of the setup again. Okay, let's come to advanced thin film solar cells as the first topic I would like to discuss. They are considered to be generation 2 solar cell materials based on inorganic thin films, and so far cadmium telluride and copper indium selenide are systems which are under technology production, and for some time also amorphous silicon was at this position but didn't succeed now because of the lack of performance. And the advantages of the systems are you have a cheap deposition technology, low material consumption, cheap materials, and it was always considered to be economic competitive, but somehow there are only 2 technologies which have made it, and they are not really in real competitiveness to silicon solar cell. There are some disadvantages that we have limited resources from some of the materials like indium here, or you may have hazardous materials like cadmium in the cadmium telluride or cadmium, but this seems to be more a political discussion. Okay, that means overall to get a high efficiency thin film solar cell, it seems to be rather easy. You just take an ideal absorber, a perfect front contact, and a low ohmic back contact, and everything is fine. But so far, very many materials have been tried, and the results are not very promising. And I would like to discuss what certain problems of these thin film technologies may be. The problem is, this is a paper which has been produced by WADA, and he has investigated how much of the different materials will be available. And then you see that those materials which are used, they are not that much available as you would like to have it. And there are very many others, here with the green ones, which seem to be available in big amounts, but they have not made it to high efficiency. And therefore, there's still a need to get a better insight what determines the performance of photovoltaic systems. Okay, if you look at the expected conversion efficiencies for photovoltaics, you have usually this Shockley-Queisser limit, depending, also it's the expected theoretical efficiency depends on the illumination, and we see that, let's say, for one single absorber layer, the band gap of the photovoltaic absorber should be between 1 and 1.5 electron volt, and for those systems which have been intensively investigated, the efficiency which are theoretically expected are nearly reached, but the maximum band gaps would be something around 25%. Better it would be if you go to 2 semiconductor layers. That means you take one band gap in the range of 0.1 to 1.2 electron volt, another one at 1.5 and 2 electron volt, add these 2 semiconductor absorbers on top of each other, and with that, efficiency beyond 35% can be reached. And this would be, I think, one way one has to go for thin film absorber materials to really be competitive to silicon, trying to go to a cheap thin film tandem structure for the future. However, there's no reason that physically this couldn't be possible. These tandem cells would be also very promising, but we need to optimize now new wideband semiconductor materials. And so far, we didn't even succeed to optimize a number of alternative thin film materials. Therefore, it's very important to understand what is really the limitation in thin film solar cell performance. But I think this is the way to go, and especially for the people in thin film technology, this is the way we have to go. Let's say start with an idealized thin film device structure. And this is a PIN structure where you have an absorber layer in between an N-doped TCO and the P-doped TCO, which is arranged like that. The thickness of this absorber layer must be larger than 3 over alpha, where alpha is the absorption coefficient. And then the diffusion length of your charge carriers in the semiconductor must be also larger than this thickness. Then you have the chance to get all the charge carriers out. This is basically, for very many good semiconductors, not the problem. The big problem is usually the interface behavior. That means if you have this contact between your absorber material and then the different contact material, then you may have here interface defects, and these interface defects, they are efficient recombination centers. And in addition, they may destroy this nice alignment in the semiconductor band edges here in the conduction band and here at the valence band edge, as you would like to have it, to have the maximum photovoltage, and then you get a lower photovoltage of the system, and this will be part of the problem. That means these interface defects with the related band alignment is one of the big problems, and in addition, so far we don't have really a good hole conductor. That means a P-type contact, P-type TCO layer, which we need for having a device structure like that developed. Okay. Now I go some steps back to cadmium telluride. We worked on that for some time. It's not the most popular semiconductor material in the moment, but you can learn a lot from the development of this material, and this has to be transferred also to new type of absorber materials if you want to go and get similar developments. If you look, this is a typical setup of the cadmium telluride solar cell, let's say 10, 15 years ago when we started to work on that, where we have a rather thick cadmium telluride layer, a rather thick cadmium sulfide layer, and if you look at the current voltage curve, you see this here, this rollover phenomena, and that in the optical absorption spectra and the external quantum yield, you have a strong absorption of the cadmium sulfide layer here, which you have as an intermediate layer between the TCO and the cadmium telluride. And this reduces efficiency at that time to something like 10, 12% in efficiency. Okay, we did a number of experiments and we got it set up. This is here a CSS type of deposition chamber, which we built up under ultra vacuum condition. That means we have here same condition as we have it in a production line, where we can move the materials and the sources across each other. And as you may know, the cadmium telluride is deposited by a closed-space sublimation process, which has the advantage that it's a type of PVD deposition set up, but the source and the substrate is very close to each other. It means you can go to rather high temperatures and get very nice deposition properties. Okay, this is how it looks like in reality. Again, here the chamber and here the deposition setups. And if you now look at this band energy diagram of the cadmium telluride at that time, this was determined by this combination of thin film deposition and interface studies by XPS. Then you notice you have here an interdiffused regime, here an interdiffused regime, and also on the back contact an interdiffused regime. And I already said the cadmium telluride is rather thick with 8 micrometer. It means an optimization of solar cell would be to have here just, let's say, a thickness of 1 micrometer, because this would be good enough from the absorption coefficient. You need a nice ohmic contact, which you didn't have. And the cadmium sulfide, as I've said before, is making problem because it absorbs the light. And the question is, why do we need this cadmium sulfide in addition and need this interdiffusion at the interfaces? And this is very simple to be investigated by, here we had a, let's say, a simple cadmium chloride activation setup made, where we just took a PVD source very close to the sample and heated that up for the typical condition of the activation. I did forget to mention that if you do the deposition of the cadmium telluride solar cell and you forget to do the activation, the performance of the solar cell is basically 0. It means this is what you have here. That's not 0, but it's very weak. Then you need the activation treatment, and with that you activate, and it's the reason for the name, the solar cell, and you get very nice efficiency. And the question is, what happens with this activation? As we have done the XPS sputter depth profile here before the activation, you see the different layers very clearly separated. And if you activate, you see that you have this interdiffusion at the phase boundaries. Yeah, and this is what you need to do. In a non-activated system, you have a lattice mismatch semiconductor on top of each other, and therefore you have defects at the interfaces. And by the interdiffusion which you reach by the activation, these defects are distributed over a certain thickness, and it means at the interface you don't have a high concentration of defect states. And this is schematically shown here. We have originally this high concentration of interface defects. After the interdiffusion, the graded junction, these interface defects are gone. And this is something what you need to do for all thin film solar cells. It means you have the chance either to have a lattice match system, which is very hardly to get, or very hard to get. You may have this interdiffusion process, or you may have a reactive interface, like for copper indium selenides. If you just take an absorber layer and put a TCO on top, you have the defects at the interface and the system will not work. You need to get this interdiffusion, this graded, this fuzzy design of the interface done. That means the activation of the interdiffusion leads to a reduction of the interface density of states, and this is very important for a combination of a thin film material with the contact phase being a TCO or whatever. And here you need the cadmium sulfide, because you will not have an interdiffusion with the cadmium telluride with the TCO, which will overcome the defects. Okay, second thing is, why do we have this thick layer? As here we already have reduced it to 5 micrometer. Why do we don't get 1 micrometer thick cadmium telluride solar cells? Now, yeah, if you look at the structure of the cadmium telluride grains, how they are formed for different boundary conditions. You notice, and this is what you very often see, you have a strong three-dimensional texture of your grains, which are not oriented to each other. That means there are no specific orientation of the films to each other. And then if you have additional processes, in the cadmium telluride there's an etching process which uses to etch down from the grain boundaries and then forming a tellurium layer here. And this tellurium layer leads then to a short from the backside, also the back contact to the front contact, and as a consequence, the performance of the solar cells is bad. What you would like to have is a very defined orientation of all grains in a very similar flat arrangement as it's shown on the right. Then even etching and deposition of other materials will not distort the interface, and you have a compact layer. And this is also a big problem for very many thin film deposition technologies of absorber layers, because if you do the deposition at lower temperatures, you have very often a very nice flat film, but then the quality of the grains is not high enough for good optoelectronic properties. If you go to a higher temperature in annealing steps, then you get the grains healed, or the defect states in the grains healed, but with that you get also a rearrangement of the grain orientation, and with that you get the chance of getting pinholes and stuff like that. And this is easily to be seen if you look at the scanning electron microscopy results of cadmium telluride film morphology at different temperature. You see here, you see the different grain texture which we get. We get at a rather low temperature, we already get a reasonable grain morphology with not too much or too many pinholes. If you go to higher temperatures, the grains get larger, but you get also more pinholes. And only at very high temperature, you get again a morphology you would like to have. It means it tells you very much that there's a certain, let's say, sweet spot for the deposition of the film in the right way, that you get the right texture in the films. And if you look here, this is the texture, the 111 orientation we have here and here. No, we have here texture in 111 orientation. Here we lose the texture. And this is the range where you get high efficiencies of the solar cell. And the reason is that in the 111 texture of the cadmium telluride, you form a stacking fold, two-dimensional stacking fold from a zinc blender to Wurtzite to a zinc blender structure. And this means you have two-dimensional defects in the material. You see this also here in the XPS, not XPS, in the X-ray diffraction results. If you do then the activation, you get rid of these stacking folds, you get a nice orientation of your grains in the material, and this is what you need. Again, you have needed a certain trick in trying to control the morphology of the cadmium telluride films, and this is very hard if you start with a new material. Then it's very hard to get this right orientation reached from the very beginning. Okay, with that we have now a thin film cadmium telluride of 2.5 micrometer. We have here the cadmium sulfide. We have substituted by a cadmium oxysulfide, which we do by sputtering of cadmium sulfide in oxygen atmosphere. With that, we lose the absorption of the cadmium sulfide. For the back contact, we have now a copper oxide layer. This is already 3 years old, the results. At that time, we had 15.2%. And here you see the quantum efficiency. We have mostly lost this absorption on the front side. We have to confess we are not that good like First Solar, but they have basically done the same things. They have lost here the cadmium sulfide absorption by going to a different type of window layer. Actually, I don't know what they did. And they have also obtained a better current voltage curve by an improved back contact. That means basically cadmium telluride has improved a lot with that, but there's still one big thing to do, and this is that the photo voltage is only, let's say, 0.85 volt, and you would like to expect something like 1.1 or 1.2 volt. And there's still the interface designed to be optimized for our cells, but also for the cells of First Solar. Okay, that means if you want to go to future solar cell concepts with inorganic thin films. You need a highly absorbing, non-critical inorganic semiconductor. There are a number of which we have investigated during the time. There are some like copper sulfide, copper oxide, and tin sulfide, which look very promising from the very beginning. But in these cases, the P and N dope transparent contacts, we didn't find any procedure yet which allows this interdiffusion at the grain boundaries. And if you just, as I've said, take the absorber layer, put a TCO contact to that, you always have the defects, and there's no photovoltage in the system. And the second one, important thing is a controlled nucleation of growth on a glass DSO substrate. That means we need to understand how, in a thin film deposition technique, we can control the nucleation and the growth, that we get nicely oriented layers of the films on top of each other. And finally, the doping and defects of the absorber layers must be controlled, which needs an extended heat treatment, annealing after you have done the deposition. And with that, you shouldn't destroy or disturb your morphology of the thin films. Looks easy, but it's really very hard, and so far none of the new absorber materials have made it to a competitive status. That means I think here also you, with the expertise in thin film deposition and vacuum coating, may think about better procedures to control this growth and nucleation and interface formation of thin film absorber materials. Okay, with that I come to the second part of my presentation, which will be on photoelectrochemical cells for fuel production. The thing what you want to do is you just take a semiconductor, put it into an electrolyte, and if you illuminate that, hydrogen and oxygen comes out, and the semiconductor should be stable. It's basically, if you look on the process from a photovoltaic converter requirement, what you need to get in a solar cell, where you have the electrons and holes coming out with a quantum efficiency of close to 1, and you have to maximize the photovoltage in the system, it's not that different from what you need to do for photoelectrochemical cell, because also there you have to optimize the quantum efficiency inside the absorber material. Then you have to adjust the photovoltage of your solar converter, that the hydrogen and oxygen evolution will be possible, and then you need to minimize overvoltage loss due to the electrochemistry on both sides of the system. Okay, just shortly, what are the energetic conditions for water electrolysis? You need to consider the splitting of the electron-hole pairs. That means the difference in the electrochemical potential of electrons and holes to be larger than the hydrogen evolution potential and oxygen evolution potential. But you have to add here this electrochemical overvoltage, which are about 100 millivolt and 300 millivolt for the hydrogen evolution and the oxygen evolution. But then you have to consider also that you don't want to operate your system at the open circuit photovoltage condition, but under the operation voltage, which is the maximum power point. It means you need another 200 or more milli-electron volt, and this means your converter must provide a photovoltage in the range of, let's say, exceeding 1.6 volts, let's say maybe even going to 1.9 volt. And that means if you look at what the photovoltage usually is, which will be provided by a solar cell, which is smaller than the band gap, minus 400 millivolt, but this only for the best solar cells. For most materials, you will be happy if your photovoltage will be the band gap divided by 2. Okay, and that means if you take a one absorber material with some passivation layer, as we needed here too, and the catalyst on both sides, and go to, let's say, normal 2 electron volt or larger than 2 electron volt band gap material, then you would consider here as the efficiency which have been reached, and here these black arrows are the photovoltage which have been obtained for this, let's say, best solar cell materials, and none of them reaches more than 1.9 electron volt. It means this tells you one absorber material will not do it. You need to go to tandem and triple devices. You may go to 3-5 based triple devices to amorphous silicon cells, or try to find new type of semiconductor junction with the right band gaps. And this brings you to the same duty as to go for an advanced thin film multi-junction cell. It means if you want to go to water splitting, you need to find photovoltaic absorber materials which can be combined to a tandem cell in a proper way. It means these are the same research direction for both applications. So far, we don't have that available. Just another consideration, we have here the absorber material. Again, we need this yellow surface passivation layer, which is an electronic passivation to get rid of the defect states or the interface states, but it's also a chemical passivation because you would like to avoid that your electrochemical contacts will react with the semiconductor. That means you have to optimize the PV performance of this absorber system. You have to optimize the electrochemistry for the charge transfer reaction, and for that you need to avoid unwanted side reaction, which means you need to add catalysts which will allow for the hydrogen evolution and the oxygen evolution. Okay, that means we have started, let's say, from a fundamental point of view, p silicon and platinum. This is the p silicon hydrogen terminated 111 surface, nice lead pattern. Then we put platinum on top of that, which we used in different ways. We used PVD deposition or CVD deposition. But whatever we do, the photovoltage of this system is very low. Then we have tried the same thing with gallium phosphide, which is a larger material. Again, trying to get a nice lead pattern, 100 surface, then using a nitrogen plasma to get a surface passivation in a proper way. And again, also here the photovoltage is very low. And this tells you how important this surface and interface engineering is also for the photoelectrochemical water splitting process. And this is shown here, where you have to consider, this is just shown for one semiconductor, but as I've said, you need a tandem structure for getting into photovoltage. The first thing what you have to add is a passivation layer, a chemical and electronic passivation layer. And then, if you want to use the electrons coming from the semiconductor for hydrogen evolution, then you think, okay, let's take platinum as a catalyst, but catalyst is a high work function metal. It means the Fermi level is somewhere here, and as a consequence, the electrons move down from the conduction band to the Fermi level, and you get completely, you're losing completely your photovoltage, which is provided by the solar cell. What you need to do is, you have to assign a contact layer here, which has a defined Fermi level, which allows to keep the photovoltage of the solar cell, and with that, the Fermi level of platinum will be aligning, and then the chemical reaction will be possible. It means you have to consider that the platinum is not just a catalyst, but it's also a contact material, and this has to be aligned in a proper way to get things working. Okay, for trying what we can do, we have worked together with the people from Jülich, who are specialists in amorphous silicon solar cells, and they have provided us with different type of tandem, triple or quadruple cells, and these are all the electrochemical current voltage curves you can get for these things. And if you look what the system will provide, they provide a maximum power point of voltage in the range, let's say at around 2 electron volt. And if we put these now into solution without any bias voltage, without any potential start, and look at the current voltage curve, this is shown here, then we see with an amorphous silicon microcrystalline triple cell, we get a solar to hydrogen efficiency of 9.5%. This is no trick, nothing. It means solar radiation in and hydrogen out. Telling us that the procedure is basically correct, our ideas is correct, but with that, amorphous silicon cannot be much better than the 13% in efficiency. We need to go now to new absorber materials. Okay, I have to skip the lithium intercalation batteries part. Okay, and come to the conclusions. There's still research needs for advanced energy converters. And good performance can only be reached with multi-layers of heterostructures of electronic device quality. This means this defines a need for improved known and novel materials. We have to find novel materials which should work. The nucleation and growth of thin film deposition techniques must be better controlled for optimized microstructure evolution. The contact formation of heterocontacts must be better understood on an atomistic level. We have done some work on some of the materials, and we have understood that you need this interface interdiffusion to get things running. The electronic density of states must be known across the hetero interface. It governs the electric potential distribution, which at the end defines the photovoltage of the system, and it governs the electronic and ionic charge transfer, which defines at the end the photocurrent of the system. Interface engineering strategies must be developed to passivate the surface chemically and electronically, and there are new characterization tools now available which allow a better insight by in situ and in operandi analysis. Okay, that means this is just, there's still a lot to do in film technology, but if we can do this, there's a strong contribution and a strong hope that film technology will help to get better solar cells, photoelectrochemical fuel producing cells, advanced battery systems, thermoelectric materials, and so on. But we need to understand somewhat better what we do in the deposition process, and if we know that, then I think we have a bright future as vacuum coaters and film deposition people, and with that, I would like to thank my co-workers, the funding from DFG, BMBF, European Community and Industry, and you for your attention. Thank you very much.